that was, so we were trying to understand matrices in terms of functions, in terms of linear functions, right? And we want to see how that can help us and to understand either of the two things. Okay, so we had these things called linear functions, and this we had well motivated and such. Linear functions from R2 to R2. R to R, we kind of, well, we think we kind of understand when the continuity condition at least is given. Or yeah, but this linear is a very strict linear definition in the sense that this has a lot of conditions. This is it's a lot of conditions. So if f is, so what we mean is that f of, so this is, I am writing this as a vector, meaning that as a thing in R2. Okay, and then you have y. So this thing is equal to, so you know what happens, right? So basically this thing, and this we are doing, so one way, I mean, it will help you to answer questions about linear functions, but you could see it as trying to understand matrices in a more in context, matrices in context. Okay, so yeah, and also there is another thing where multiplying by scalars also splits. So these two both, not just one of them does not imply the other. Okay, we are using both. Yeah, so it is this. Okay. So we are basically looking at these kind of functions. Now I don't need to give you examples. You can, there are you can just think of several examples. You pick any good function from R2 to R2, like a rotation, you pick a reflection, you pick a translation, all those functions. Yeah, vector formally. So okay, so first of all, you can take here, you can take x and y to be tuples of numbers. Sorry, you can take x and y to be pairs of numbers. Okay, you can, because it's just an R2. Okay, but to think of them as vectors is really helpful. But for us, what is a vector? Let's vector. Clearly speaking, right? Yeah, vector. So I'm basically going to say that to every point in R2, we associate a line that starts from the origin to that point in R2, and that line segment is a vector. Okay, so vectors are a set of line, but this is not the correct definition, and this is not a good definition. Whether it's correct or not can be, after spending some time you can understand, but it's not a good definition. Set of line segments passing through the origin. So I've said line segments, it really matters. So different line segments is a set. So different, no other thing I've said. So different line segments will give you different vectors. Okay, so as from here you can understand that every vector is nothing, you can view it like a pair of numbers, right? So this carries two information about the two dimension, and so all these three red lines are three different vectors. So that can be taken. Does anybody know, but this is not a good definition, does anybody know a better definition of vectors? I just say different, which is not useful for us, because for us everything will have to start from the origin, so it's not really needed, because we're just going to treat them as pairs of points, pairs of numbers and lines through the origin only. But a different definition, anyone? Okay, that's just yeah. No. So see, basically it starts like this. it's kind of like you have this R2. Okay, so we start with R2, right? Now, if you're starting with R2, if you're studying R2, you're going to be studying line segments in R2. That's just like for step one, right? And step two is you will have to look at sets of line segments in R2, subsets, special kinds of subsets, and whatnot, right? So you'll be looking at the set of line segments in R2, right? This is certainly correct. You can understand a lot of context. You will be looking at lines. If you're doing geometry, you'll be looking. If you're doing physics, you're looking and so on. But then for certain purposes, you may not be interested in, you may not be interested in distinguishing parallel line segments with the same length. Okay. So that is the thing. So we may want to let go of this distinction of parallel line segments with the same length. If there are two line segments which are parallel to each other and they have the same length, then we may not want to distinguish them. Now this can happen for several reasons, right? You may want to call them the same thing. So if there is a quantity like force, which has a direction and length, then the force associated to this line segment and this, maybe you would call them the same things because it's the same force, like vectorially, direction wise and length wise. The full information of force in both those line segments is the same. So you want to let go of this distinction, right? And so you basically want to put an equivalence relation. So you have this L that is the set of all, this is even a problem, maybe you can say in equivalence relations, you will see set of line segments in R2. And now you want to put an equivalence relation on this set. Okay. And what is that equivalence? So how do you write that in high school terms? Equivalence relation. No, so what I'm interested in is equivalence classes. So let me say it like this. So there will be an equivalence relation R, and you will say that L1 is related to L2, which we will basically think as L1 being equal to L2 if L1 and L2 have the same length and same direction. Okay. Yeah. That you have to check. Yeah, right. So basically we are letting go of some distinction. And so we are trying to call things same, which were earlier different. But when you want to call things same, you have to make a rule maybe, right, under which you're calling things same. Now that rule which you are using to call different things same, that rule must be an equivalence relation, right? Because otherwise it will violate the fundamental things about what same means, right? Like if you're calling L1 and L2 same and L2 and L3 same, then L1 and L3 you should call same. And that's we put them in the as saying that it should form an equivalence relation. So when you're trying to form new notion of equality, then that new notion must be equivalence relation at least. Otherwise it's an absurd notion of equality. Then it's not a good categorization, right? So and same, so let me just say slope maybe is a good word. Slope L1 equal to, now you should check that this is an equal. Whenever you're introducing a new relation which you want to capture things like this, then you should check that it is an equivalence relation. And the equivalence classes are the vectors, right? The equivalence classes are the vectors, means that every class, meaning the set of lines which have same direction and same length, they are the same vector. And that's what we say, right? A vector, when you can translate a vector, it's the same vector, right? It doesn't change. So that's what That's what vector is. It's a equivalence classes under this relation. That's a precise definition, and also it captures the entire history. It captures the entire thing, where it comes. Maybe that's not how it came, but that's how it was formalized to have come. Okay. So you can check that it's an equivalence relation. This is also a good. Right. So now this is fine, and this is. I mean, vectors have a much more general meaning, but that's what it is for us. And vectors in R2 are these things. So we were looking at these things called linear functions, right? We were trying to understand these. And then we were looking at 2x2 matrices. 2x2 matrices with integer entries. No, not integer. This is not combinatorics or number theory, maybe with real entries. This obviously we at least know in the definition. We know this is just things like this. Now, what is connection? Okay. So, anybody wants to say? We are done last time. Maybe you have thought and read about it later. So. So no one has a thought. So we are trying to put a connection between these two things. Yeah. So, yes, right. So that's the first thing. That's the first connection, right? That every. So if you think this matrix is a linear function. So this we understand. So by linear function, we mean linear function from R2 to R2 for us. Okay. This is certainly a linear function. Now this view is going to be so useful that you cannot imagine. Like when you have a matrix and if you see it as a function, you will see a lot of things. The function composition, matrix multiplication, associativity, so many things just follow because now you're seeing it as a function, not just as a, as a table of numbers. This is fine. This we understand. Every matrix gives a unique function. But can we go in the other direction? That was really the question last time. And that's a decent problem, like show that every linear function is a matrix. Yeah. So given a linear function f, you want to find a matrix. So given, I'm just putting it in a different way, just a more logically clear way. Given f, you want to find a matrix ABCD, okay, such that these are the same things as functions. Put it more specifically, f of x is equal to, this is an R2, remember, and this also is an R2, is equal to this times x. Now this you understand, just to this is the thing. Every linear function can be written like this, and this completely makes it analogous to fx equals to this will be the cx. When they were numbers, they were numbers. When this is vectors or tuple pair of numbers, then this is not a number, it's a matrix. So matrices are the new numbers. Okay, they are the new numbers that we have to. No, x is just a column, right? It's just like one x is like 1 2 or something. Like, okay, so x, we have written x in the column way, just a natural. No, it's like a column. Yeah. So how do we do this? This is the burning question. This is the thing too. Then we can try to see how it understands us to help linear functions, because the linear functions will have a very concrete representation, and that we can use maybe. What? This? No. So I don't know. You can call it a matrix equation. Yes. So f of c. So if f of 0 comma 1, this could be 1 comma 1, right? So this would be something like a 1 comma 1. Now you may write it as a, you should write it as a column, right? And then you want to find ABCD such that this holds, but not just for this 1 and 1, but for every x. You see, okay? For every x, it should work. So now you understand what exactly this means. It's just a column, and this is also just a column. You can write it as a row also. You can write this x here, this side as a row. Doesn't matter. So how do you find the ABCD? In general. Okay, so maybe it's a little tricky. So now, so let's come to a concrete linear function. Yes. Yeah. So basically this will become like if x is x1, x2, or you write it as a column. Yes, but then how? But then what's the guarantee that you can find an ABCD which works for all x? That is the thing, right? That's not immediately clear, right? This you want to be equal to. So this fx, now this is a very strange thing, right? You don't know. Yes, that's right. It is f of x1, x2, but then that also has two, it outputs two numbers. So you have to write it as a column. I mean, I could write as f1, x1, x2, but it will just become more cumbersome, right? But it's not clear. How do you, like, maybe if I give a function, if we take a particular linear function, then we can understand that it will work, and then we can prove. Yes, right. This comparing thing will not help you to prove that in general you can find ABCD like this. Existence, yeah, it can be used if you choose the vectors more carefully, but yeah, it can be used. You have to choose um, the right vectors, maybe. Let's take a particular example. We can take example. So we can take rotation. Okay. So we can take f to be the function which is rotation. You can take rotation by 30 degrees. Okay. First, you guys have to show me that this is a linear function. Don't maybe try not to use complex numbers. You can use it, but yeah, just try to not use complex numbers. That will give you some good insight. Maybe show that f is linear. First of all, you have to know this, right? Whether it's linear or not. So why is rotation linear? Okay, yeah. So that's what we'll try to derive in a very natural way. That's the goal, right? So that's right. So we will get there. But can we geometrically show that rotation is linear? Geometrically, just by reasoning geometrically. Obviously, by coordinate geometry, you have the formulas and you can use them, which is good. But you see, geometrically, so this is a so rotation by 30 degrees will be a function, right? Because the input will be the input point, and the output will be the point where it goes after 30-degree rotation, right? So yeah, so for function, it's clearly a function from R2 to R2. So that is clear. So now we are viewing these things as functions. So it's already a good thing. No, just by geometric reasoning. So that certainly you can do if you derive the formula, because then you can just check that it's a linear. But can we see it? That is the yeah that can be done certainly. So we can take it. So that's right. So if so, x. Let's take x to be 1 comma 0. So this is the x. And but yeah, we have to take some other point, and that we cannot negotiate. So we can take that point to be this. We don't know what that is. No, this is the other input. You have to take two inputs, right, to prove that it is linear. So whether you add first or then apply the function, or apply the function and then add, it remains the same. So it respects the linear structure, which is the additive structure. That's why it's called linear. So this we don't know. We don't even need to write anything. Just yeah, but it's better to not write, because we're basically doing it geometrically, right? So I mean, we don't even need to. Yeah, but right. So how do you show that this is linear? And this idea is used in a lot of minimization, find the shortest distance, congruence proofs in geometry. These ideas are used. Fermat point, I remember. Rotations being. What exactly do you have to prove? You need to understand that first, and then yeah, f of x is the rotated point, right? So let's write that. Yeah, that's the output. So let's draw the output in green. So this is so maybe f of x is somewhere here, right? So then this would be no, we don't want to use trigonometry. With trigonometry, we can do anything, right? With given sufficiently large amount of time, you can do anything. Right. Okay. So that's a feature of this function. So you were saying that basically this function composed 18 times is the identity function. This is the identity function, but that it doesn't mean it's going to be linear. The order of a function has nothing, or 12 times something, I don't know, you check it. 12 times, yeah, 12 times. But that is not the point. This 30 is not important. It will work even for irrational uh, degrees where you will never come back. Yeah, so certainly this turns out to be periodic, but linear functions in general need not be periodic. You have translations which are not periodic. Well, they are not periodic in R2. If you translate on a torus, like if you have a donut and you kind of do translations, you will see will come back. So that's a different thing. Okay. But on a R2, you don't come back when you do translations. Well, on a sphere also, just simple example. Maybe. But yeah, on plane translations are non-periodic. And so that's the thing. I mean, if you understand like this, then you can, from here, if you know the matrix, then you would know that this matrix to the power 12 is also going to be this. Once you understand this thing, and that you can understand now, this helps a lot in the theory of matrices. In particular, it will show that this is invertible matrix, and so on. You can find it in its inverse, in front, and so that's what happens when you see it as a function. But what we're trying to show, let's try to show that. So if this is x and this is theta, this is where it comes. Okay? Similarly with y, let me just call this x prime. This is the output. Okay? Then similarly with y, you can go, this is like a geometry question, very simple geometry question. It's very important, I think, to do this to actually feel that it is linear. So I didn't want to do like this. Okay, so this is the y prime. Now, what do we want to show? We want to show that if you add x and y, which means if you look at this end of this parallelogram, or you could take the intersection point of the diagonals, it does not matter, right? It's the same thing. But yeah, we just take this. So it's just very simple. Right, and that's the point x plus y, right? So that's x plus y. Now if you apply f on this, you want to show that this is not this. This is a little, well, I don't know what it is, but something. Okay. Now when you rotate this, so any red green angle is 30 degrees. If it y prime, any something prime, that is 30 degrees. Yeah, this is a bit yeah, it will be here like this. Like this. This is x plus y prime. This is f of x plus y. So what do we want to show? Well, we want to show that this is a parallelogram, right? So let me write that just. So we want to show, but this is absolutely obvious. We want to show that x prime and f of x plus y, y prime, and obviously 0, this is a parallelogram. No, but this is something else happening here. These are not some of the vectors, right? This is not the sum of the vectors. right? This is fx, this is fy. That's what we want to show. We want to show that this is a parallelogram. Do you guys agree, right? Because that is what we want to show. Because then you'll be done, right? That this will be addition. That f of y plus f of x is f of x plus y. Hmm. 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 Yes, you can. No, but the point is the circles are changing. Yeah. But yeah, it's similar. You can use, so as Raghav is saying SS, you can use some sort of congruency. Right? You can use congruency. That's the simplest way. So yeah, but the circle thing, because the circles are changing and you don't know the radius of the circle x plus y in terms of, yeah. So yeah, so that is the thing. So then how do you use congruency? X plus y, f of x plus y. Okay. This is angle. So this origin and f of x plus y. Yeah, this angle is 30, right? Right, right. Yeah, so something like that you can do, right? And that's, I think, precise also. Right. So you can just say that it's kind of congruency, right? Yeah. Uh, SAS. Mhm. You don't need to join the segments because, as you said, the length remains the same, right? So yeah. Mhm. Mhm. Mm. I no, but the lengths are also there, right? The lengths are also same. But in any case, you realize that this is a simple thing which you can do, right? So, mm, yes, yes, you can just do it by several ways. So as you're saying, yeah, but you can, so you can do it, right? So show this by simple angle chasing. Okay, so complete. That's it. It is very simple. You can say this in several ways. But then you see, this makes this fact that it's a linear function, it makes it completely obvious, right? Like it just, we have proved it, we've kind of seen it, right? Now the task is to, um, now it's a linear function, so you can see it, okay? You can see that it's linear. Now that it is linear, how do we use it to show that it has a, find the matrix for it? Okay, so we want to find a matrix. for F. Now you see, you guys can answer this question in several ways, maybe, but actually find a matrix for this is not a good question. Okay, I like to think about this like this, where matrix just comes as a way of bookkeeping and accounting and kind of, okay, just a way of arranging things. But the idea is that it can be described by 4 numbers comes first. Okay, and this is like this. So suppose I want to find out where 4, 5 goes after rotation by 30 degrees. Suppose I want to find out. Now I know something. I know it's a linear function. So why don't I use it? Before I didn't used to use it. Before I used to look up the formula because I didn't know better. But now I know that it's a linear function. So if I know that it's a linear function, I won't do this. I will just try to find where this goes after rotation 4, 0, which is maybe very much maybe simpler. And then I will try to figure out where 0, 5 goes after rotation. I mean, that's the next thing I should do, right? If I have proof that it's linear, and then I can get a good, and then the 4 also I can pull out, and the 5 also. So all I need to know is where 1, 0 goes after rotation and where 0, 1 goes after rotation. These two, if you want to call it two, though it's 4 in some sense, pieces of information is enough to figure out everything. And this you can do for any linear function. That's why linear functions are important, interesting. You just need to know where 1, 0 goes and 0, 1 goes. And once you, yeah, it becomes, and that's the whole point of linearity. Yeah, when 1, 0 and 0, 1 you can find them, right? But then you also see that if you want to write this, people said, okay, let's write this in a better way. So we are like, okay, we can, no, but remember f of 1, 0 is a pair of numbers, right? So people said, okay, let's write it like this and multiply this like. Okay, and that is exactly what's happening. Let's make it more clear. Make it clear. So point is that this 1, 0, we know what this is, f of 1, 0. What is it? Some root 3 and something. Half is the cosine. Yeah, something, or maybe root 3 by 2 and 1/2, right? 30 degree. Yeah. Hey, cos 30 comes first, right? Yeah. I mean, I have forgotten trigonometry, but you should not forget. And 0, 1. So 0, 1, yeah, where does that go? So that angle will be 120 degrees with the origin. You can figure out 120 is, yeah, cos, right, minus half. No, minus half, no, but sine, no, but sine is positive, right? Yeah, this is cos and this is sine. Yeah, so that's half. And this one is, yeah, this is positive. Yeah, root 3. Now you see, you just need these 4 numbers and these will be the entries of your matrix. And how the matrix just comes as a language for here, as a good means to keep things. I mean, that's how matrices came, in some sense, you could say, as a tool for just collecting pairs of numbers and treating them like one number. So now, I mean, you could replace x1 comma. Yes, and matrices help you to treat them like one variable. Matrices, like matrix, helps you to treat so many n square numbers as a single number up to the extent you can. Okay, 1 minute, my battery is low. Yeah, we're almost at the end, but I have to do it because I can't take risk. It can end. It can. I have to also finish some work. 1 second. 1 second. Yes. So if it is this, then you will just write it as root 3 by 2 comma half. And you see, you can do this. You can do this for any linear function, right? And not anything special. Once you know the value of f of 1. Okay, so we were just saying that for this rotation thing, I mean, for any x comma y, right, you will basically end up with something like, I don't know, some a comma b times x and some c comma d times y, right? And this a b c d does not depend on x and y. This a b c d is universal. Once you find these a b c d, you are done, right? And we know how this AB, what this AB is, right? So this A comma B is nothing but it is f of 1 comma 0, at least the way we have done, right? And this is nothing but C comma D. Isn't this wonderful? And this will work for any linear function. I mean, just do it. Don't believe me. But you can see, like, I didn't use anything about a rotation. I just use the fact that it can be recovered from 1 comma 0 and 0 comma 1, but that just used, we did that by just using properties of linearity. So now you get the matrix. This is the matrix. I mean, this is what a matrix multiplication is defined. This and, oh wait, what happened now? What happens now if I no, so if I do, so how should I write it? That is the question. So if I want to follow the convention of matrix multiplication, then I should write it like this. Otherwise, I can just do my own convention, right? I can multiply from the left, and that's also a convention actually, which is accepted. But you see, it just arises, matrix multiplication just arises naturally as a means to compress this information and arrange it in a good way so that the operations we do kind of are reminiscent of what we do for usual numbers. Obviously not exactly, that's why just some. So we're just laying this new concept, but using older language. Okay, so this basically proves that with any linear function f, any linear function f, if f is a linear function, then essentially what you have is, this is so is this something wrong here? 1 second now. So let me just cross check it. I think because I'm getting some kind of a contradiction. Let's just run the thing again, no problem. But this, so as we did, this will just be x times 1 comma 0 plus y times, oh my god, the rats, y times 0 comma 1, right? This, no, so if this is a comma b and this is c comma d, then the way I should write, then let's write this again if you want. You can write this as ax plus cy comma bx plus dy, right? And this is very clear now that the matrix should be this. Yeah, so there was something wrong I had written earlier, I think, or maybe now it's wrong. Now it is correct, right? So that earlier thing was wrong. So you see, this column is the important thing. This column is the image of f of 1, where 1 comma 0 goes, the first unit vector, and this is the image of the second unit vector. And that's all you need to know. So not just that there is a matrix, but the entries of the matrix have this meaning. And that's all you need to find the linear function. We have a matrix representation. Okay, so that's it for today. Mostly theoretical. I gave some 2 problems to try and we did a problem. We learned about disconnection, we understood rotation, we saw some geometry thing. Let me give some problems which you can try with to prove some facts about linear functions which you can prove, some good questions, but maybe you can use matrices to your advantage. That now that you have matrices, because matrices are a very concrete thing. Those are the linear functions that you understand completely, which kind of you understand very well. But now we have proved that all linear functions are nothing but matrices. So that's the beauty. So here are the things that I want you guys to try. So the number one thing is, if, and this is fundamental thing, if f is injective, then, so all the questions I'm giving, I'm only giving them in terms of f linear function. The matrices you have to bring in and apply if you want to. Surjective. Not just because the domain and range is same, that is not true. Okay, because you can give injective functions from an infinite set to the same infinite set, which is not surjective. Like n going to 2n from naturals to naturals. But in this case, it does not happen. Injectivity implies surjectivity. And in fact, surjectivity also implies, so you can prove that. Now, these are some very, maybe, yeah. So here is another one. If f is not injective, then actually it kills some vector. Then there is a x such that, this is simple. So you can try. Now the third question is like, okay, maybe I can give this, maybe you can think of this. This is regarding, what was it? Yeah, this is, yeah. Find matrix for reflection. You can take x-axis. If f takes lines if f takes, so if f of line through origin. So if this is the like this is like an input, it's like a set of inputs, right? Line through the origin, line through origin be equal to line through basically vector in our definition. So if f is a function that when it takes input a line, I'm not saying a line segment. If it takes a line, then it will send this line to some other line. If f is such a function, which line it sends, that's not given. Just if it sends, if it just permutes, if it just sends lines to lines, then does this imply that f is injective? Sorry, does this imply that f is linear? Because colloquially maybe linear means lines to lines, but you will have to see. I think the answer should be no, but you'll have to think. Maybe it's yes. Okay. So these questions I can immediately think of. Now you can, yeah, you can try this question also. Let f be from, now it's from R2 to R is linear. This is even an easier problem, right? In that sense. R2 to R, or you can turn it up. You can take R3 to R2 if you are bored, if you find this too easy. Is linear. Show f cannot be injective. Okay, show that f cannot be injective. Now, yeah. Now this is another beautiful question. So let f be linear. Okay. Show there exists a degree 4 polynomial or you can find one, like I'll give an example. Like when you took the rotation by 30 degrees, right? Then for that, what did you guys do? So what did we do? We said, okay, you take this and you take this, it becomes 0. It is absolutely 0, right? Now, what do I mean by this, right? So this just means that this is the 0 function, right? This function that when it takes a vector v, it up or takes a number, whatever, then just does this. This is 0 for all v, right? That's what we just proved. This means that this polynomial x to the power 12, right? When you input this function in that polynomial, then it is 0. Right? So basically, there is some times you can compose the function and add the function, some of the compositions, you will get 0. You'll get the 0. You can create a 0 function. Okay. That's what happens in this case, that you compose it 12 times and then subtract it. With composing 0 times, you get the 0 function. And so I want you to show that this can be done for any function, any linear function. Okay. Show that there is a 4 degree polynomial, degree of a polynomial such that p of f is 0. Okay. Or let me just write this in a, so I mean here you have a 12 degree polynomial, but I'm saying that is too much. A 4 degree polynomial should be sufficient. So what I'm saying is that there is show that this changing it, making it like simple language, show that there exists numbers, some a3, a2, a1, a0, such that this is f composed 4 times, f composed 3 times, I mean, there could be AI could be 0 also. Show that you can find such things. Okay, so you can think of your knowledge of system of equations and try, because now you have matrices representing them and not think. Okay, so yeah, let's keep this for now. Okay, try these problems, note them down, or you can see them. Just note them down, maybe that's better. Path problem, what path? No, but that is done, right? Oh, that problem. Okay, okay, that I will do. Yeah. Right. That's pending. We have not done that. So tomorrow we can do a counting class. So tomorrow I think I will do, because already we have missed a lot of things. So yeah, tomorrow we can do counting. I have some other relevant counting questions, different types. So tomorrow we're a little late again. So we'll do at 9:30 or 9:45. Hopefully 9:30 हो जाएगा. Not even, yeah, 9:30. I'll have dinner and then 9:30 p.m. we will do. I'm just saying combinatorics because we will see. We will do counting first, and then if we get time, we'll do some other kind. Yes, yes. So this is Thursday. I have to write. Right. I'll just write a mail now so that I don't. Okay. Yes, yeah. Those things I have not done much. We did some problems here and there with coloring, but okay. So tomorrow, let me split the class. We can just do some two counting problems and 2 3 coloring, or coloring problems. Let's do, and then coloring problems are very fun. Surely we will do. Okay, tomorrow we'll do 2 3 colorings and counting. And also I'll give some problems which you can try, like I gave today.